Okay, so in your 6.2 note packet, it says Newton's law of cooling states that the rate of change in the temperature, see, when it says rate of change of temperature, that's a derivative, is proportional to the difference between the object's temperature and the temperature of the surrounding medium. Now, what that means, you may not have heard that worded that way. This is like the room temperature. And we're going to abbreviate that T sub R. We're going to call the object's temperature T. And the rate of change of temperature is dt, but we're going to use a capital T for temperature and a lowercase t for time. Because you want to see the rate of change in the temperature over time. So if it's proportional to, that's dt equals k times, and it's proportional to the difference between the object's temperature and the temperature in the room, or what they say by the surrounding medium. We're going to look at things like oven, like the oven temperature, or a freezer temperature. So then you're talking about what was the starting temperature in the freezer, you know, or whatever you might have. Now, if you're pulling, say, a cake out of the oven, where are you putting it? You're putting it in the room, okay? But if you're putting something in the freezer, then the surrounding is the freezer. So you got to think about that. All right, so let's look at example 6. And again, we're going to end up filling the entire page in this space. It says, let Y represent the temperature in degrees Fahrenheit of an object in a room whose temperature is kept at a constant 60 degrees. If the object cools from 100 degrees to 90 degrees in 10 minutes, how much longer will it take for its temperature to decrease to 80 degrees? Let's change that Y to capital T, okay? So that we can do this in the format I gave it. So the room temperature is 60 degrees. So that's T sub R. And we know it went from time is 0, that's 100 degrees, to 10 minutes later. And we want to find the temperature, or we want to find the time, actually. We want to find T when the temperature is 80 degrees. So here we go. Using Newton's law of cooling, the change in the temperature is proportional to the difference in the temperature of the object and the temperature of the room. So here's the deal. We know the room temperature is 60 degrees. And you want to keep the degree symbol or not. It's completely up to you. So now watch what we're going to do. This is a differential equation. It's a differential equation because it has a derivative, and we have to find capital T. We don't have enough information yet to do that. So watch what I'm going to do. I'm going to divide by the T minus 60, and I'm going to also multiply by dt. So what I'm doing, and we're going to formally cover this in the next section, but we are going to separate the variables. So I have dt over t minus 60 equals k dt. So now, if I want to solve this for t, I'm going to integrate. Now you need to be careful. I have more than t down in the bottom, so when I integrate dt over t minus 60, I have to do u substitution there. So I'm going to let u be t minus 60, so du equals dt. So I'm doing the integral of 1 over u du, and on the right side, that's kt plus c. Okay, if I have the integral of k dt, that k is a constant, so that's kt plus c. Now on the left side, that's the natural log of u equals kt plus c. Now, we worked on this last time, on Thursday. What you're going to have to do is, this is a logarithmic equation, and I need to convert it to exponential form. So this is going to go e to the kt plus c power equals u. But what was u? T minus 60. Okay, then you also remember that this is actually e to the kt times e to the c, and that's t minus 60. Okay, this was that exponent property. A to the m times a to the n is a to the m plus n. So I've got the right side and I'm moving left. E to the c is just some constant, and then I add 60. So I'm getting t equals ce to the kt plus 60. And I have two pieces of information here. I have 0, 100. This is little t, comma, capital T. Okay, it's time, comma, temperature. So we're going to plug in the first point. This would be CE, bless you, to the 0 times k power plus 60, and that's 100. Okay, again, I'm plugging in that time is 0 and temperature is 100. Well, e to the 0 is 1, so that's C, so C is 40. Well, that's good, because now I have T equals 40e to the kt plus 60. And notice I'm making my T's with that little tail on it, because I don't want to mix up my T with my addition sign. So either make it cursive or a little tail or something that distinguishes your plus sign from your temperature. All right, so I plugged in 0, 100. That helped me find C. Now I still don't know K, but I have another point. So let's use the 10, 90. So this will be 90 equals 40e to the 10k plus 60. This is also a problem where we're going to want to use the store feature that we did before. Remember how we did the store feature? So I subtract 60, and I get 30 equals 40e to the 10k. Divide by 30, and that's 0.75 equals e to the 10k. Take the natural log of both sides. Then I have the natural log of 0.75 equals 10k, divide by 10, and I'm getting negative 0.028768. So my formula is t equals 40e to the negative 0.028768 t power plus 60. All right, so when you're doing this and it says use Newton's law of cooling, you're going to use, this is the given formula. Whether it's given or not given, this is the one you should be able to find in your notes to use. Now I'm not done, let's reread the problem. It says, if the object cools from 100 degrees to 90 degrees in 10 minutes, how much longer will it take for its temperature to decrease to 80 degrees? So we want the ending temperature to be 80. So let me give you a head start and see if you can solve that. You're trying to solve for t, the time t. It's the exponent. So you subtract 60. Divide by 40. Are you getting t equals 24.1? Now, why is that the wrong answer?
Because it says how much time.
Yeah, okay, do you see that? We've done it correctly, okay? T is 24, but it says how much longer, how much time has elapsed?
That would make it 14.
Yeah, okay, 10 minutes has elapsed, and so it's 14 more minutes. So be careful with that. It will take a total of 24 or 24.1 minutes, but it's 14 more minutes.
So when we have a test over this, we're gonna have like 12 of those?
No, like one.
Okay.
Just one. All right, now flip your paper over, and we're going to do 2 extra examples. But they're not Newtons, okay? We're doing one of those. Okay, here's another application. To this is exponential growth. It says, if $12,500 is invested at 5.75% compounded quarterly, then how long will it take for the money to grow to $20,000? Well, you want to play the game, what do I know? Well, compounding quarterly uses this formula. There's 2 compounding formulas. One is this one and the other one's PERT. PERT is only used if it says compounding continuously. Okay? That's when you'll use the PERT, that's the second example we're going to do. So A equals P times the quantity, 1 plus R over N to the NT power. So here we go. We want it to grow to 20,000. It's starting at 12,500. The interest rate needs to be converted to a decimal. And quarterly is 4. So when you divide by N, N is the number of times that it's compounded. All right, so what you're going to do first, divide both sides by the 12,500. And I'm getting 1.6 equals, then do the number inside the parenthesis. And when I take 1 plus 0.0575 divided by 4, I'm getting 1.014375. I would discourage you from rounding, because if you round, it'll get further and further away from your actual. Now, what do I need to do if I want to solve for t? Yes, let's take the natural log of both sides. And then you can bring down the power. Now, you can take the natural log of 1.6 and then divide by 4, then divide by ln, that decimal number. So I'm getting about 8.2 years. And, you know, if you think about it, you guys are young. The younger you are that you can start investing money, saving money, the wiser it is for you later on. You have to put less money aside than if you think, oh, I'll just do it later. Well, life happens, and then it's harder. You have to put more money aside. All right, last example. Yeah, Bethany?
For that, could we like store that number?
Yes, absolutely. And then on your paper, you can round. Yeah, that's fine.
And you want us to note that we stored it, right?
Yes.
If it asks for us to round, you want us to just round at the very end?
Just at the very end. And good question. You guys, money is always rounded to the nearest cent. That's like common sense. Pun intended. Let's just get it.
Oh, you're so funny.
All right, if $8,000 is invested at 8%, then how long will it take to double the amount if it's compounded continuously? So I perk up when I see compounded continuously. That's PERT. A equals P times e to the RT. And again, some of this is just, it's inference. And if you know, I think most of you have taken the ACT, there's some inference on some of the, like the reading section. They come out and ask you things, and then you have to infer what that means. So the inference is you double the amount. They didn't come out and say what it is, but we're smart enough to know what is the double amount. 16,000. I mean, if you start with 8 and you're going to double it, you can figure that out. That's 16,000 equals 8,000 e to the 0.08 t power. So if you divide by 8,000, you're going to get 2 equals e to the 0.08 t power. And let me tell you something. They actually could have gotten away with telling me nothing about the amount of money put in except that it's double. You get that? That I could have said, okay, say I want to put in some random amount. How long will it take at 8% to double it? You would call this P, this amount would be 2 times P, divide by the P, and I still have 2. It works out every time that way. You can triple the money, and I could know nothing about that principal amount and still be able to do it. All right, so you take the natural log of 2. Now notice, if it's a base of e, ln e always cancels. Then divide by 0.08, and I got about 8.7 years. Okay, then take out your 6.2, worksheet number 1. I did tell you with number 5 that your half-life, it wasn't on the paper, but it was in your textbook. Plutonium was 24,100 years. All right, are there any of those from the board, Elena?
2.
Number 2.